Now we are going to talk about balancing nuclear equations. All right, these are actually pretty simple to balance. We're not looking for the elements to be balanced like in a chemical reaction. We are looking at the masses to be balanced, right? Law of conservation of mass, can't lose mass. And the number of protons, or the charge, essentially has to balance on both sides. So this is our mass number at the top. Notice the mass on the left side of my reaction. So I'm looking on the left and the right of the arrow, just like regular balancing. My mass is 238. So that means that the mass number on the right side also has to equal 238. So notice 4 plus 234 is 238. Good. The atomic number on this side is 92. That means I have 92 protons, or like positively charged particles of those particles. So on the right side, these also have to add up to 92. So I have 2 and 90, which is of course 92. So essentially the goal of balancing these reactions is that the top numbers have to add up and the bottom numbers have to add up. Left versus right. So example number 1, I will talk through 1 and 2 with you, and then I would pause it and try the other ones. Okay, so kind of ignore C through E really quick. Okay, so it says write the balanced nuclear equations for each of the following decay processes. I've got U-235 undergoes alpha decay. So I start with U-235. The symbol looks like this, 235. I look up uranium. Uranium is 92 on the periodic table, so its atomic number, or number of protons is 92. Okay, so when it's written this way, like U-235, this is the mass number. Okay, that's the number that goes at top. So it says it undergoes alpha decay. Well, that means that one of my products is alpha, and then I have to figure out the other one. So the way that we do these is you're going to balance with your decay product or reactant or whatever it is. Okay, so I would just figure out the numbers first. So, well, I got 235 on this side, and I have a 4 from my alpha, so this has to be 231. And then I've got 92 down here, and I've got 2 here, so this has to be 90. And then I would be like, oh, look at my periodic table. What is the element with atomic number 90? Well, it is thorium. Okay, so what you have to do is solve for those numbers and then figure out what element that is. And in this case, it is thorium. So we're trying to solve for that daughter nuclei. Okay, same thing for B. I've got C14, which means carbon with a mass of 14. Carbon on the periodic table has 6 protons, always. It says it undergoes beta decay. So that means one of my products is a beta. So I did 0, -1 beta, or you could do a little E. And I'm going to look at the numbers. So my top numbers, well, this has no mass. So that means this has to be 14, right, in order to get those to add up. And this is 6, but this is -1. Remember, we're adding them. So this has to be a 7, because 7 plus -1 is 6. Okay, so that does count as a negative number. So what is number 7 on the periodic table? Well, it's nitrogen. So the daughter nuclide is nitrogen 14. All right, so I would pause it here and do C through E. And then I am going to talk through them. So if it releases a gamma ray, it doesn't change the mass or anything. This is how you represent your gamma ray. It means the molecule is going to be exactly the same. One way that you might see this indicated is that, like, this means high energy. It has a little asterisk there. I won't have you write something that's just gamma ray, because usually gamma rays just accompany other reactions. This was just to show you that it doesn't change the mass or the charge. Okay. Strontium 83 looks like this, releases a positron particle, and if you solve for the other one, you get rubidium. And iron 55 undergoes electron capture. Capture would mean it is a reactant, so you have to actually add it to the iron. So it should be on the left side, which means my product is going to be, this was 26 -1, so 25, which is manganese. Okay, so solve for the element left.